we will be ready to go. Go ahead and take it, Jeff.
Okay, welcome to our weekly sessions here. Al and Dick are going to do a bang-up job again today on oscilloscopes, and I just wanted to pitch next week. I'll be doing a diesel exhaust after treatment sessions, 3 sessions. There is a link to some homework. You could do a little pre-work in the questionnaire, which I will again put up in the chat. The very last section of that where you see a piece of graphic, there's a link to a Ford document that's over 200 pages. And I've given you a targeted reading assignment. So study ahead, you'll be at the head of the class. Take it away.
That's important. I like to be at the head of the class. Okay.
Al, could I have just 1 minute?
Sure.
Guys, those of you that asked for the files that I promised to send you, I discovered this morning that there was a glitch in the PowerPoints. It's my fault. I didn't wait until they uploaded to OneDrive before I tried to share it, and somehow it just goes into an endless cycle. I acknowledge that, and I will fix it. You should have received the 2 PDFs, which was the 2 handouts for the classes, but I will resend the PowerPoints when I finish the meeting here, and I apologize for the inconvenience. If you have any questions, email me. We'll talk about it. Go ahead, Al. Sorry.
Okay. Well, let's get ourselves going here, and that's okay. Like we did yesterday, if you have questions or comments or whatever, if you could put them into the chat, and Dick will monitor that, and some of the questions he'll be able to answer directly, and if he wants to throw them out, he'll throw it to me. So let me share my screen. Okay. Yesterday we were looking at voltage waveforms, and I tried to get across the idea or the concept that if you could, that you can use the oscilloscope pattern as a method for teaching something. Now, you know, if you think about this pattern with just a minor little detail, you can use the same pattern, or will get a pattern which is very similar off of a relay, off of an ignition coil, off of, you know, all sorts of different things. So again, you know, a lot of times what I would do is I would start, and I would always talk about, you know, and use a whiteboard if I could, and say, okay, now, you know, what is this showing here? And you'll notice I don't have it labeled as a PCM, and I don't have the DSO placed there, but I do have the positive and the negative. So that, and again, the more times you repeat that, the better off you are. The other thing that I have sometimes done is said, you know, there are times when we need to, let's get, okay. In a lot of the stuff that I draw, a square or a rectangle is a voltmeter, and a round is an ammeter. And of course, what am I trying to show here? I'm trying to show that because on the ground side, I'm basically at 0 volts, and on the B plus side, I'm at, you know, 12.6 or some number, that there will be a voltage drop across this coil of wire, and that voltage drop is not there if the contacts are, can't do that, Al, if the contacts are open. And then, of course, this would go down. So I think that's a concept and something that I would constantly go back to. One of the things that I think is really an important, and I don't even want to call it a concept, but one of the things which is really important here is your ability to show the students why they want to learn DSOs. Now, for some of you who don't use DSOs, maybe you're in the same bracket. You need to learn, or you need to figure out why you would want to teach them. Well, there's a couple of things that I usually do, and one of them I did already, and that was showing using cursors how the individual voltage changes and how the time changes. So that's one of the things that I think works exceptionally well. And let me go back to my Pico. And just to refresh your memory here, the Pico the pattern you're looking at right now is amps in red, voltage in blue, and this is off a 2007 Toyota. Yesterday I tried to say that when you want to zero in on voltage, zero in on it. And there's a couple of different ways to do it. One of the ways was the way I did it yesterday. Let me give you another way. If we go up here to the top and we hit the plus, now you can see the plus is on my cursor. And if I click on it, everything grows. Now I go up and I get the mitt and I drag this where I want it. And again, get the box, the zoom overview out of the way. Okay, and you can see I've got a little bit of the current waveform there, so I can just run it down there. Now I've got just the voltage waveform. And I think so that there's multiple methods for doing it, multiple ways to do it. Okay, and don't be afraid to try different methods. One of the things that I think works out really well is to discuss with a student how a fuel injector actually works. And a lot of times I'll stand in front of the room and I'll have my arms around me and I say, there's a coil of wire, and then I squat down and we have enough current flowing through this coil of wire, it pulls the pintle up. And when you pull the pintle up, you are changing around the magnetic field. If you change around the magnetic field, you also change the current flow. And what happens is you generate a pintle bump. And there's the pintle bump. And then, if you want, you can zero in on the pintle bump, but be careful. And here I'm going to show you why. See, when you try to expand it too much, there's the pintle bump, but it becomes very, very difficult to see. So again, if we're talking about this, what we maybe want to do is something like this. Now there, the pintle bump shows pretty well. What is the pintle bump? Well, when that slug, which is actually the pintle, moves up, it moves up and it changes the magnetic field. If you change the magnetic field, you change the current. So what happens is you get this little bump. That is the spot that the fuel injector actually opens at. Now let me go back to full screen. This little bump over here, right there, and again, you really can't do this to it because you can barely see it, but there it is, okay? That is where the fuel injector actually opens. So on the voltage waveform, we can see where the fuel injector, closes. On the current waveform, we can see where it opens. And then what I'll do is I'll spend a little bit of time and talk about command. This is the command. So in other words, on my fuel injector, it begins right at that point, and you can see that both voltage goes down, and because now when the voltage goes down, you have a difference in voltage on the two sides of the coil, current begins to flow at the same point. And then if we take another cursor and we put it right over here, okay, that's the command. And when we say command, what do we mean? Well, the PCM is saying that I need to have, and I'm going to write it down, 2.372 milliseconds. And you don't have to carry it out. You can just say 2.3 milliseconds, or even 2.25, whatever. You can call it whatever you want. That's the command from the PCM. Now, the next thing is to say, well, okay, if that's the command, then where did the fuel injector, or how long did the fuel injector actually stay open for? So there's where it closed, and here is where it opened. Now you'll notice that I've gone to 1.537. Well, now wait a minute. How come it's not the same? Here's a way to look at this. How much fuel is needed? 1.537 milliseconds worth of fuel at this speed and load and temperature and everything else. 1.5. Well, wait, for the fuel injector to flow that amount of fuel, in theory, you would think that the fuel injector should be open for 1.537 milliseconds. And if you started with brand new fuel injectors, you'll find that the numbers are almost exactly the same with new fuel injectors. But obviously, this car has got over 100,000 miles on it. Knowing my granddaughter, I would seriously doubt that anything other than putting gas in it has ever been done to it since her other grandfather gave it to her a couple of years ago. So these things are probably pretty dirty. Well, let's do a comparison. We started with 2.3, rounding it off, and we're at 1.5. That's a significant difference. So in other words, it took the PCM putting out a signal of 2.37 for the fuel injector to actually flow 1.53. Significant difference. If you want a number, a millisecond, a couple milliseconds, maybe 2 to 3 milliseconds at the most, indicates that the fuel injectors are relatively clean. But you know, when we look at something like this, it's not uncommon to have a full millisecond. I mean, this one's almost a full millisecond difference. Now, remember, we're going from 1.5 up to 2.3. So, you know, we've got 0.8 milliseconds worth of difference there. And that difference indicates that things are dirty. Now, you might think to yourself, well, I don't really have this information readily at hand. Okay, let's go. That's not where I wanted to go. Let's go back over to here. And let's go over to automotive. And let's go over to actuator. And let's come down to injector petrol. And put multi-point voltage versus current. Now, this is not a pattern that I have taken. This pattern comes off of the inside, what comes with the Pico. Again, what you have in the beginning here is an explanation, and then you have a diagram. Okay, now that diagram, as it sits there, you really can't do any real easy measuring on it. Although, see, they were real kind and they put 0 all the way at the end over here. So 0 shows up really well. But watch what you can do. If you go down and you hit the actual Pico button, it'll toggle it. Once it's toggled, now look what you gain. You now have the ability to say that the command for this particular fuel injector was 6.18 milliseconds. It's a hell of a fuel injection, by the way. But anyway, okay, it's 6 milliseconds. And then, well, what's the difference? Let's just call it an even 6. And then we move our cursors and we realize that we have 5. So are these fuel injectors clean or are they dirty? Well, they're actually pretty dirty. And again, I mean, eventually you're gonna store patterns, and the more patterns you store, the better off you're going to be, because you're going to be able to rely on them all the time. That's a big thing to do. But don't forget, inside the Pico 6 automotive software, you have got patterns which you can play with. And you can play with on the screen. With that, I'm gonna, that's not what I want. I went the wrong way, I'm sorry. Okay, I'm gonna flip over to ignition. Ignition has changed, and from a realistic standpoint, if you take a look at the vast majority of that's still injection. You know, let me do something here. Sorry about this. Okay. I wrote down some numbers that I needed to switch to, and I put the wrong number down. I put down 31 rather than 39. Anyway, okay. If you take a look at most of the automobiles now, you really don't have a secondary available, because the secondary, you know, what's the vast majority of cars? They're coil on plug. There are still a few that are coiled near plug where you have a small spark plug wire, and that's okay. So now you can measure your secondary. But you've got to get the students to recognize that there's 2 bits of information that we need to figure out on all of these cars. And well, actually 3. The first thing is, did a spark actually occur? The second thing was, how long was primary current on for? And the third thing, and the most important thing, is how long did the spark actually last? So the paddle probe has become the method. And this is capacitance coupled. Now, by the way, when we talk about capacitance coupled as opposed to inductive coupled, and when you inductively couple something, you get accurate voltage and time. When you capacitive couple it, you're just getting the probe near the magnetic field. So how close are you? Well, it's who built the coil. So it's not voltage accurate, but it is in fact time accurate. Put it on a small probe, we connect it to the DSO, and we use engine ground again, and we come up with a realistic pattern. So now I'm going to go back to my Pico, and I'm going to open up. Wait, let's see. Boom. Okay, this is a realistic pattern, first of all, and what this pattern shows us is what's the primary on time and some current flow and a few other things. The top in blue is actually the signal from the ignition coil. So in other words, go back to this. Yeah, it's right here. Here's where the DSO is placed. Here's the ignition coil, and as the ignition coil in the ignition module, this is no longer the DSO, it's now the module. As it opens and closes and opens and closes, the voltage signal that you get will be this square wave. And again, I want to zero in on the square wave, so let's do that. This is the beginning of, if you're old enough, dwell, and this is the end of it. Okay, so what actually happens here on this particular car is we need to put some cursors on. We need to look at it and we need to say, okay, how long was the command signal? Okay. Now the command signal on this is about 1.1 milliseconds. So it's actually pretty small. It's not a tremendously long thing. What we don't see or can't see here is how long did the spark actually last. You can't see that off of this. If you get rid of this and you say, well, maybe we can see it on the current flow, the answer again is no, we can't see it on the current flow. So what we have to do is we have to say, okay, let's use a paddle on it. So if we go down and we put a paddle on it, the first thing we do is we totally ignore the voltage. So in other words, this says I'm up at 1.6 volts. It doesn't mean anything. It means absolutely nothing. Where is the spark? Where does the spark actually begin? Where does the spark actually end? So now we can take cursors and we can put the cursors and the manufacturers have for years, and I hope you're teaching this. If you're not, please teach it. The manufacturers have said from an emission standpoint, we need to have a spark in the cylinder that lasts between 0.8 and 2.0 milliseconds. 0.8 to 2.0 milliseconds. Notice this one is call it 1.8. So in other words, it's a full millisecond into that 0.8 to 2.3. If you realize that the only information we have available now is the paddle, the command signal, and current flow. With those three pieces of information, the student has almost everything that he needs. The reason I say almost everything is there's one other thing, and I should have done it while I had the paddle up here, so let's put the paddle back up. With the paddle back up, we can absolutely say there was a spark. And the reason we can say there was a spark comes to right at this spot right here. If you have an inductive kick and then you have a voltage which starts higher than the supply voltage, you know there was a spark. You don't know the quality of it. You don't know how, much about it, other than if you look at the entire thing, you can look at the amount of time the spark actually lasts. Very, very important thing for the student to get. How long did the spark last? And how long did I actually have and did I actually have some current flowing across the spark plug gap? This spike up here indicates that we did in fact have ignition. And when we compare it, and you got a 4-cylinder car here, what I do is I take the paddle and I move the paddle from one coil to the next, to the next, to the next, in the hope that what I see is the same pattern with approximately the same voltage. Okay? You can also, on some cars, and this is kind of an unusual one, see this little right there? That's when primary current actually turned on. So in other words, we're getting a little bit of an indication of it. And you could, with the student, again say, okay, how long did primary current last? And we can go and we can put a set of cursors on here and actually take a measurement. Okay, you'll find if you can see this primary signal here, that this primary signal will typically be between 2.5 and above, or above 2.5 milliseconds. And this shows it, yeah, it's at 3.18. So we get the necessary information off of different patterns. Was there a spark? Yeah, we get that off the paddle. What was the command in terms of, not in terms of voltage, but what was the command signal in terms of time? Excuse me. And then how long did the spark last? And that's the bit of information. And the nice thing about this is you don't have to sit down and measure, and remember 10,000 different things. What you have to remember is primary on time should exceed, call it 2.5 milliseconds. Most cars are over 3, but call it 2.5 milliseconds. There's a couple of GMs that are lower. And how long did the spark last? Between 0.8 and 2.0. And was there a spark? That's the important information. Okay?
Al Plater from Centennial mentioned, Al, that he says try comparing an inductive crank sensor on top of the coil attached to your scope. If you're teaching, it works better if you put a metallic duct tape around the coil too.
Wait, say that again. Say that again.
He says try comparing an inductive crank sensor on top of the coil attached to your scope. If you are teaching, it works better if you put metallic duct tape on the coil.
Okay, I guess I don't understand.
We can discuss it in the afterglow here.
I think what that's going to do is basically to be the same thing as the paddle. Maybe you'll get a higher signal, and maybe that's what you're actually working on. Okay, in the remaining time which I have left, which is not a whole lot, but we'll do it anyway. Okay, let's talk a little bit about fuel pumps, because one of the things, again, I'm trying to get across is why do you want to teach the use of a digital storage oscilloscope? We've looked at how we can actually build something. We can also look at fuel pumps and realize that fuel pumps can be responsible for misfires and drivability and everything else, and that the important thing is pressure and volume. But we also have to can realize that if we have a method of calculating pump speed, that by calculating pump speed, we're using a DSO in another one of these applications. In other words, to be able to say to a student that we're going to find a repeating pattern, we're going to look for it, we're going to divide it, we're going to multiply, and that's going to equal the speed of the pump. And then we go through a couple of different things. And I'm going to do this, you know, on a, not a live, but on one of the Picos, just so you get an idea of what we're talking with. This is the basic formula, though, is real simple. We try to see how many humps we have. And you can see that this kind of has a little bit of almost like a sine wave to it. We count the number of humps. What you're actually looking at are the number of commutator bars that are on the armature. Typical, we have 8. It's not always the case, but typically we have 8. So then what you do is you count the number, you count 8 humps. So you go out and you count 1, 2, 3, 4, 5, 6, 7, 8, all the way across. And when you're done, you look at the amount of time and put it into milliseconds, 0.009. We divide that into 1. Why 1? Well, 1 equals a second. So if we divide 1 divided by 0.009, in this particular example, we come up with 111. If we come up with 111, that's 111 rotations per second multiplied by 60 seconds. Gives you an RPM of 6,600 RPM, or yeah, 6,660 RPM. Now, there are methods where you do it all in one shot. And let me explain to you why I personally don't like that. If you're doing this with a student, and especially if you have your whiteboard handy, walk the student through it. So that what you do is you say, okay, how many humps did you have? 8. Put a number 8 up there. Then what's the time between the repeat? And they can actually sit down and count it, 0.009. Okay, now, when we say 0.009 seconds, that's how many milliseconds. You'll notice on this example here, I've got a 2 millisecond per division. So the 2, 4, 6, 8, 9, there's my second. There's 1, 2, 3, 4, 5, 6, 7, 8. So 8 to 8. It means 1 complete rotation. Don't look at it and say, well, it's only, you go to the beginning or you go to the end. No, you go to your peak. So where your peaks are, either peaks or valleys, and count 8. And then we put that on the board. Well, it's about 9.009. Have them get their calculator out. 1 divided by 0.009 equals, and by the way, you know, in my day, people carried, or after my day, people carried calculators. Well, they're doing it now, right? Every one of these kids has got a smartphone in his pocket. Have him use it. And then we divide it into 1, we get 111. Put the 111 on the whiteboard. What does that mean? Well, why did we divide it into 1? We divided it into 1 because 1 represents a second. Well, then 0.009 goes into 1 111 times. That means we have 111 rotations in a second. We multiply it by 60 seconds, we have the RPM. Okay? Now, these patterns are very, very easy to obtain. You know, all you have to do is just, you know, and let me, not there. I want to go over to here. Now I want to go there. Okay, so we're going to go down to actuators. And we're going to come down the fuel pump. Okay, here's your explanation. There's your current probe, a real nice picture of the current probe, and connected to one of the leads on the fuel pump. Okay, and then there's our pattern. Now again, I want the pattern to be live, so I'm going to toggle. I shouldn't use the word live. Live's not the right word. I want the pattern to be measurable, so I'm going to go down and I'm going to hit it. And when I toggle, when I toggle, what I get is a live, I keep saying live. I get a pattern. And what is this pattern? Well, let's just do a little measuring here. So 1, 2, 3, 4, 5, 6, 7, 8. Okay. So there, you know, by the way, you can see you're at just about 10 milliseconds, but let's actually put a cursor on it because I want to show you what the beauty of a pico is. Okay, and now I'm going to put the other one. What did I do? Is that the one I counted? 1, 2, 3, 4, 5, 6, 7. No, this is the one I counted, 8. Okay, so that's the total number, 9.83 milliseconds. Now you get the student to get his calculator out on his phone and say, okay, how do we do this? We take 1, we divide it by that, blah, 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 and you do all the multiplication. Or if you cheat, look down here at the lower right-hand corner, okay? A pico automatically calculates the RPM. So in other words, it automatically does all the multiplication and the division using 9.83 as the delta, or the difference between the two cursors, and comes up with the RPM. I don't think you can get much better than this. This just makes it so much easier. So you can sit down and you can do this. And then, by the way, I always think it's a good idea to throw in one which is bad. Now, this is a pretty easy one to tell the difference between good and bad. Let's just look at the pattern. Just forget what's written on the screen. Look at the pattern on the right. And remember, this was in about, call it, 0.009 milliseconds. Well, look at this one now. Well, first of all, we're at 5 milliseconds per division. And this vehicle came in with reduced pressure, reduced volume. And if you calculate this pump out, this pump is running at 1,700 RPM, which is utterly ridiculous. Okay? Now, let me go back to this and back to this. And let me unshare my screen. Okay. Guys and gals, if we have any here, it's really an important, concept's the wrong word, but it's a really important thing to get students used to using a digital storage oscilloscope. The earlier you put it into your curriculum, the better off you are. And then show the students at the beginning especially, just give them a couple of simple little things to do. You know, hey guys, let's learn how a relay works, or let's learn how an ignition coil works, or let's learn how a fuel injector works, and let's use the DSO for it. Send them out, have them get the patterns, have them come back with the patterns. If they don't have the patterns, fine. Use the Pico Automotive 6 software, excuse me, and do it that way. But give them some simple things. Say, hey, especially if you have the advantage of the kids in front of you. Who's got an older car? Let's see how good the fuel injectors are. Go out and measure current, measure voltage, and bring the pattern in, and we'll calculate and we'll determine how good the fuel injector is flowing. Now, this is another way, it's not a big leap from command versus actual to fuel trim, because that's really what you're looking at. I mean, if it takes, and my example I had before was, if it takes a signal, a command signal of 1.5 milliseconds to get, no, I said that wrong. If it takes a command signal of 2.3 milliseconds to get 1.5 milliseconds worth of fuel, that's fuel trim. What fuel trim has done is fuel trim has told the PCM, hey, I want this amount of fuel based on my oxygen sensor. So as that fuel is being injected, it just increases until the oxygen sensor gets satisfied. And that's what they're looking at. New fuel injectors, remember, flow a tenth of a millisecond or so, somewhere in that neighborhood. And then as they get dirtier, they get worse and worse and worse. If you have someone who continuously or periodically uses cleaner, you'll find that it'll stay around 1 to maybe at the most 0.3 of a millisecond. Okay? Jimmy, I guess I'm done.
I was not going to interrupt you.
No, I can see it's 133. I got my timer on my screen.
You were on a roll, so I was going to let you go.
No,
Dick, do you want to address any of the questions that you answered in there before I stopped the recording?
Most of the questions we were able to answer in the chat. A couple of them were asking about how do you choose the humps that you select, and the answer is, as you said, you must find 2 exact repeating humps, set your cursors on there, and then that's the number of segments in your pump by counting them, And that's the time difference between your two cursors is where you calculate your pump speed.
Yeah,
Or
this gets a little hard, guys, when you have brand new pumps. Okay, the older the pump is, or once the pump is worn in, you can take a brand new pump and drive it for 250 to 500 miles, and it'll come back, and it has now worn in enough that you'll be able to see the difference in the humps. I mean, can I share my screen again?
Sure. I'm
Okay,
still recording too because this is still good.
okay. Look at this. Look at this pattern. This is, by the way. Let me just fill in some blanks. This was a Ford Taurus, came in on the end of a tow hook into our shop at the College of DuPage when I was still working there.
I don't think
And
we're seeing
you
it
know,
yet now.
Yeah, there's
We're
nothing
not
on your
sure.
screen. No screen sharing at the moment.
well, there is on my end.
We can see them in your glasses, but that's really kind of small.
Yeah, that's hard to pick out.
start and stop again now.
It's only got one hump.
There it is.
Okay,
There
you
now.
got it now.
Yes, sir.
All right. Smart Alex everywhere. Okay. Anyway, so the car comes in, and it's a real obvious thing. I mean, we push the Schrader down and it goes, and you barely get it. The fuel kind of dribbles out, and it seems almost like you're literally getting air. So I thought, okay, this might be a good one. So I sent the students out and I said, go get me, a current probe signal or a voltage. In this particular case, it's a voltage signal, and I don't want to go into the differences here. But anyway, and I said, okay, now this is going to be a difficult one to see because it's so bad. And so what I said is, let's just make the assumption that it's an 8 commutator pump because most pumps are 8. So then we count across 1, 2, 3, 4, 5, 6, 7, 8, and we're just about where the little A is right there. Okay, we're just about there. Well, that's 5 milliseconds per division. So we have 5, 10, 15, 20, 25, 30, 35 milliseconds. And most of these pumps are usually around, 9, 10, 11, 12 milliseconds. So then I said, okay, we know it needs a new pump. So we put a new pump in. That's the new pump. Initially, though, we couldn't see the humps. We knew it was an 8 commutator pump because it even said so on the literature from the pump. But after this thing drove for a little while, you can see it picked up this curve. That's one rotation. There's the second rotation. So what we do is we look for some similarities. I can't expand this one, but see that edge right there? That's pretty close to this edge right here. So then we count 1, 2, 3, 4, 5, 6, 7, 8, and we're in business.
Al, we have an instructor that'd like you to refresh on determining dirty injectors with your humps.
We might want to stop the recording, maybe.
Yeah. If you're officially done, Al, we can stop.